Okay, hello there. This is your Chapter 4 introductory video, once again to be watched before we really dive into Chapter 4. And this chapter is really on chemical bonding. We're not going to have really any time to talk about climate change, but you can find some interesting stuff in your book to read, and if I do have time, I'll try to pull that into the lecture. Your learning goals, one of the things you have to do, and I'm going to cover this in the video because I think it's best if you learn most of this stuff on your own. I won't spend much time in lecture on it, and that is naming compounds and being able to write formulas. So it's really tedious for me to teach it in lecture, and it's really tedious for you to listen to it. So it's best for me to give you a couple guidelines and you to just spend some time on your own memorizing, and that's just the nature of it. I don't demand that you learn how to name everything. I just want you to get the basics down. I'm not going to stress that on the exam. The big part of the chapter really is this Lewis structures, and that is really the heart of the chapter, and I can't stress this enough. You have to master Lewis structures to do well on this exam, and because it ties into Chapter 5 too, and you can't do Chapter 5 without understanding Lewis structures. Ultimately, these two parts, this really is about being able to understand Lewis structures also, and there is this electronegativity and bond polarity that's important also. Here's the chapter outline. You see there's two sections. One here, 4.9, we won't cover this at all. Resonance I will cover in one or two slides simply because some faculty like to ask questions, and your final exam may very well be a departmentally generated exam, which means I'll only contribute a small number of questions to it. So I want you to be ready for a question you might see on resonance, but you don't have to know resonance for my hourly exam. So the first thing we want to talk about in this chapter is three types of bonds. They're ionic, covalent, metallic. And the easiest way to talk about these is to kind of look at these pictures here. So let's start with metallic bonds. This is one we're not going to spend much time on, and we're just going to introduce the idea. And that is, in this case, in metallic bonds, people tend to think of these like, if this is my metal here, and these are my individual atoms, okay, within the metal, we tend to think of it like a sea of electrons. And that is that the electrons we learned about in the previous chapter are not really tied to a single atom. They're free to move about, and they stay associated with the metal as a whole, but they don't bind strongly to any individual atoms. This just makes them good conductors of electricity. So we tend to think of it as the phrase that uses a sea of electrons. Covalent bonds are the bonds that are present between our covalent compounds and what you think about a molecular compound. So things like water, H2O. These are covalent bonds. And you're going to see basically these are compounds that can contain nonmetals, although this is not entirely the case, because when we think about ionic bonds, we think of a metal plus a nonmetal. And so something like sodium chloride. However, we learned about electronegativity in Chapter 3, and we realized that that classification really comes from the differences in electronegativity. Something that is truly ionic bond has to have that large difference in electronegativity. I forget the numbers your book uses, but something like greater than 2 in terms of a difference in electronegativity makes it really an ionic bond. And when you have an ionic bond, you kind of get this crystalline structure. But we have lots of salts that form with this crystalline structure in which the electronegativity isn't that different. So we tend to think of that as more of what we call a polar covalent bond, as you saw. As we're going to see here, I think we might have mentioned that in Chapter 3, that difference in electronegativity. So those are the three general types of bonds that you're going to see in this chapter. And the idea is to get a feel for what we mean by those. So here we say it again, ionic bonds are cation metals and anion nonmetals. And that is true, is that it's just that that's not exclusive. If you have a cation anion, doesn't mean we really consider that an ionic bond. But it is resulting from electrostatic attraction, and what we have is all these ions attracting each other, and you form this crystal lattice. So these might be my sodiums, and these might be my chlorides, and these might be my sodiums here. And you can see when you get into the interior of the crystal, each sodium is surrounded by chlorines on each side. Then each of those chlorines is surrounded by sodiums on each side. And you can fracture it to ever and ever smaller crystals. But ultimately, you never have a molecule. You still have a crystal of hundreds to thousands of atoms. And this creates a lattice energy, if you will. And that lattice energy is kind of the total energy that comes from that combining of charges within that structure. And you'll see in class there'll actually be an equation which we can describe this lattice energy. But one thing we'll notice when we consider, let's say, compounds like this, the lattice energy of this one here winds up being greater than this one here simply because these ions are +2 and -2, and these are +1 and -1. The opposite charges have a stronger attraction. Okay? So you actually see that. We'll look at an equation to actually quantify this. The other thing that's important is the size of the atom. If we had a cation that was this big and an anion this big, and then we had a cation that's this big and an anion this big, this one would have a stronger attraction. We can estimate this just by knowing our radii that we learned in Chapter 3. And the reason it's weaker is because, keep in mind, electrons here are attracted to this nucleus, and electrons here are attracted to this nucleus. So that distance of separation, the larger the distance of separation, makes this a weaker bond. So those are two things to look at. By far, the charge is more important than the distance of separation, all things being equal. Naming compounds is something you just need to commit time to, quite frankly. And there's specific rules for these different types of compounds and how we name them. So if we start out with binary compounds, if you will, so we're talking about two substances, two species. And in this case, we're going to start out with ionic ones. So we're looking at a cation and an anion. That's all we're going to think about now in terms of naming, because if it has a cation and an anion, we name it a certain way. Whether it's a true ionic compound or not really depends on electronegativities, but we still treat it in naming-wise as an ionic compound. It's very simple. The first word is the cation. And the second word, you just put an IDE ending on it. So it is calcium oxide for the compound I drew on the previous. Okay? Just the name of the cation, calcium cation, followed by an ID ending at the end of the anion. And that's all there is to it. You just need to spend time, learning some of the basic names. I mean, most of you probably know most of the general element names. The key is that charges must be balanced. So we're not going to have this. That's not calcium chloride. Why? Well, because calcium is 2+ and chloride is -1. So this is calcium chloride. So if someone says calcium chloride, you have to know your charges, and some of that you can garner from looking at the periodic table to know that calcium chloride has 2 chlorines, but sodium chloride only has 1. Now, transition metals. They can form multiple charges. You saw that in, I think it was Chapter 2. We had a periodic table with those charges, and they asked you to start getting familiar with that. As a result, we have to name those and let people know which cation we have. So if I were to say iron chloride, no one would know if in fact that iron chloride is in fact this or this. And that's because iron can either be +2 or +3. And chloride's -1. So there are two types of iron chlorides. So the way we name that is we actually say iron, and then you would have a Roman numeral 2 chloride. And that would tell you it's this one. Okay, so that just takes practice and learning a couple of the basic charges that are there. Now, another thing you'll see is polyatomic ions. And these are groups of atoms together, covalently bonded, but that have a charge. Okay? So not a single atom. So for instance, they're going to be nonmetals, so they're covalently bonded, sulfur and oxygen, both on the right side of the periodic table, but it has a charge. This is a polyatomic ion. And you have to get familiar with those because it's important when we talk about chemical reactions and you start to predict products and what's going to be present on the right side of a chemical reaction. You realize these things stay intact and they don't come apart typically. So if they're on the left side of the chemical reaction, they're going to be on the right side of the chemical reaction. So this would be calcium sulfate. And notice the charges are balancing it. Calcium's 2 plus and sulfate is 2 minus. And if this went through some sort of chemical reaction or it dissolves in water, you get something like this. You don't get the sulfate coming apart into individual sulfur and oxygen atoms. It stays as an ion. And this would be kind of the solid dissolving in water. So it's important that you actually start to get familiar with these polyatomic ions. And here you see, when we name them, the one with more oxygens takes on the 8 prefix, and the one with less oxygens takes on the 8 prefix. However, there's no way of knowing how many are in that series without just becoming familiar with them. So you don't know that there's only 2, a sulfate, and there's only 2, one with 4 and one with 3. There's not one with 5, there's not one with 2, there's not one with 1. Okay, so once you know there's 2, then the one with more oxygens is 8, and the one with less oxygens is 8. Now here's one in which there's 4 in the sequence. So what you do is you take the 2 middle ones, those are your 8 and 8, and the one with the most becomes per. In this case it's 4. You see there's no commonality here that 4 is always the same. No, it has to do with the whole sequence. And your one with the least is your hypoite. So that's just something you need to get familiar with. And quite frankly, the halogen group's about the only one you're going to see these was. So basically the perchlorate and the perbromate, and that's about it. You know, you're not going to have to worry about anything else. So just get that down. This is the table in your book. I hope this is not the old edition, but your table should be, if it's not 4.3, it's right around. And these are the ones you need to get familiar with. And the big ones, of course, nitrite, nitrate, hydroxide, phosphate. And these other phosphates here, there's sulfate. And here's hydrogen sulfate. There's the sulfite. Then you've got, there's the, most of these you need to know. Carbonate, there's acetate's important. There's that series of chlorate, chlorite, perchlorate. Okay, start to get familiar with this. This is one of the few positive ones. That's the ammonium cation, NH4+. Ammonia is NH3. That's your cleaning ammonia. You saw this in the lab the other day. Ammonia could be NH3, or you can have NH4OH as an aqueous solution. So just get familiar with those. There is some memorization in this chapter. Now we have the molecular ones, still binary, but we're going to use a different means of naming these, and it's key that you get these straight. What we do is we simply, for something like this, you all know this as carbon dioxide, the convention is carbon, right? And then di for 2 oxide. That's carbon dioxide. You don't use the mono prefix. We don't say, for the first, you don't say monocarbon dioxide. You do use it if it's the second carbon monoxide, that is. So that's just using these prefixes here. So you could do something like this. Dinitrogen pentoxide. One thing we do is we drop these A's when we have 2 vowels in a row. We don't say pentaoxide. I don't know why. To me, that's just as easy to say as pentoxide, but the 2 vowels in the row, some people consider cumbersome. And you'll see that in your book. And you need to get familiar with just that naming. Okay, so let's see what's next. The acids are next. Any compound with an ionizable hydrogen atom. Now, there's no way for you to recognize this at this point. So basically, it's me just telling you and you learning from your book that this is an acid. There's no way for you to look at this and know it's an acid. It just comes from convention and learning it. Eventually, you will learn something in organic chemistry that helps you understand and recognize what these ionizable hydrogens typically occur. But as far as naming it, hydro, and then replace the last syllable in the second element with ic followed by acid, becomes hydrobromic acid. Okay? And the aqueous tells you that we're talking about the acid as opposed to just hydrogen bromide. If the aqueous is not there, it's not an acid, it's just the hydrogen bromide. Oxoacids, oxoanions is something I didn't describe yet. Oxoanion is just simply an anion that has a group of oxygens attached to a central atom. So sulfate is an oxoanion. So with the oxoacids, um, the ones that were sulfate becomes ic, sulfuric acid, and the ones that were ite become sulfurous acid, and that's not on here, I guess. That's just H2SO3. It's just not here. I thought it'd be here. And that was to be sulfurous acid. That's the way we name those, and that's just, once again, something you need to get familiar with. Okay, so now we have the heart of the chapter, and that is Lewis' theory. And Lewis proposed that atoms form chemical bonds by sharing electrons to acquire electron configuration of a noble gas. The octet rule atoms tend to gain, lose, or share electrons to obtain a set of 8 valence electrons. There are exceptions to this. Remember, 8 valence electrons based on our quantum electron configurations, ns2np6. You can have that full S sublevel and the full P sublevel to give us a full energy level. Exceptions to that, of course, hydrogen only takes on 2 electrons. So there are exceptions to this, but just going to get the basics down right now. And you're going to start by just realizing the Lewis dot symbols for just the elements. It's a chemical symbol surrounded by 1 or more dots representing valence electrons. The dots are arranged around the element symbol. First 4 electrons are unpaired, then you start to pair them up. The next 4 are added to form pairs. So for example, here's carbon. It has 4 electrons. You have to put 1 in each side because you cannot pair them up yet. Okay? If you have nitrogen now, where you pair that 1 doesn't matter. This is somewhat arbitrary. This doesn't actually have any quantum mechanical significance to it. This is not some sort of region in space. Okay? It's just an accounting system. And if you have something that has less than 4 electrons, it doesn't matter which sides they're on, as long as you don't pair them up first. So you see that in the next figure here. Notice calcium has 2. Okay, it doesn't matter if it's on the left and right, top, bottom, but they use the same convention throughout. Here's boron with 3. There's your carbon with 4. And then you start to pair them up, and here's oxygen. And then you get to the noble gas configuration where you have 8 surrounding them, and they're completely full, and this is what makes them unreactive. Things are reactive when they're close to getting that octet. This is reactive because all it should do is lose that 1 electron, and it will have the same electron configuration as neon. Keep in mind there's a whole other group of electrons underneath this, because what we're showing here is simply the valence electrons, and that's it. So you have a whole other shell of electrons underneath that. This is very reactive because it just needs 1 electron, and it's going to have an electron configuration like argon. And what you see here is bonding capacities is, if you will, the number of lone electrons is the bonding capacity. So carbon has the ability to form 4 bonds because it has 4 lone ones. And this is why carbon is, if you will, the backbone of biological molecules, because it has the ability to form a lot of bonds. And hydrogen can only form 1 bond, so it wouldn't make a very good backbone, right? That's why it's always a peripheral atom. When we see it in structures here with Lewis structures as we move forward in class, you'll see it's always on the end because it can't be in the middle. It can't form 2 bonds. So this is what this whole schematic shows you here. And now lastly, this is just showing you how these octets come about. Sodium loses its electron to chlorine. They both now get a noble gas configuration. Sodium is now like neon, so its actual configuration would be this. And chlorine is argon. And that makes them happy. And this is why sodium chloride is a compound that forms easily in nature, because they make a great pair. And this is why things like this don't form in nature. Sodium magnesium. What the heck is that? You'll never see a professor write that. Why? Well, because they both want to get rid of their electrons. So they don't make a good pair. Sodium wants to get rid of one, magnesium wants to get rid of two. They need something from over here to pick up those electrons. That's what makes the compound stable. And when you look at these, now looking at this is an ionic compound, looking at a molecular compound, we see here's water, right? This electron came from hydrogen, this electron came from hydrogen, and then these 6 here came from oxygen. But they're going to share these beautifully to form a bond, so we can designate that bond either by 2 electrons or by drawing a straight line. These here are known as our lone pairs. They're not bonded. They're just lone pairs unbonded. And these are our bonding pairs. But a bond is 2 electrons being shared. And that really concludes the chapter. So make sure that you spend some time reading, looking at your outline as you go through this video. It's designed to be paused and for you to spend some time studying the material. And that concludes our video.